this video, I'm going to go over a few examples straight from MyLab for section 9.1. So in this problem, we want to factor 7r squared minus 7f squared. So the first thing I notice is that there's a common 7 in these terms. So I can pull it out to the front and say 7 times r squared minus f squared. Right, but we're not fully factored yet. This expression right here, r squared minus f squared, is called a difference of squares. Okay, and difference of squares factors like this in a general form. A plus b times a minus b. So using that form, we get 7 r plus f and r minus f. And this is our factored form. For this question, we want to factor this trinomial, s squared plus 6s minus 40. So what I like to do is I look at the coefficient here next to the squared term and the coefficient over here that doesn't have any variables. And I put their numbers here and their factors. So factors are pairs of numbers that when multiplied equal the number itself. So 1 times 1 is 1. So some factors for 40, 1 times 40 is 40, 2 times 20 is 40, 4 times 10 is 40, and 8 times 5 is 40. So next, I need to look at this sign right here before the 40. And this will say if my signs of my factored form are going to be the same or different. So if this is a plus, they will be the same sign, but since it's negative, we're going to have a plus and a minus. So now we need to look at the pairs we just wrote down and find out when multiplied and subtracted, which will make positive 6. So here I'm going to start with my 1 and 1. So if I multiply them, 1 times 1, and then I need to subtract it by 1 times 40. So when I get 1 minus 40, I get minus 39. So that's not positive 6. So let's look at a different pair. Now let's do 1 times 2 and 1 times 20. So if we do 1 times 2 minus 1 times 20, we get 2 minus 20, which gives me negative 18. Also, since this is positive, we should always start with the bigger number first, so that when we subtract it from the smaller number, we'll get a positive number. So let me switch the order for the next pair. So for this pair, let's look at 1 times 10. I'm going to do the bigger number first, and 1 times 4. So we do 1 times 10 minus 1 times 4. I get 10 minus 4, which gives me 6. So these are the pairs of numbers that I need to put here. So because my 1 coefficient is here, 1, we know that s times s is going to give us the 1s squared if we multiply them. Remember FOIL from algebra, first, outer, inner, last. So our first is going to be s times s, which will give us this 1s. That's why these two are just s and s. Okay. So then let's list our other pairs here. So now we have to decide, is this 4 or is it 10? And is this 4 or 10? So we have to choose which one. So if we put 4 here and 10 here, let's say we did that first. If we went ahead and did FOIL to multiply it across, we get s times s, or s squared, then s times 10, which would give us, or minus 10, which would give us minus 10s. And then we do the inner, so then we go to s times 4, and that gives us plus 4s. And then we do the last, so 4 times 40. Minus 40. Okay, so we see that these two terms match up, which is good. But if we combine this, we get minus 6s. So that's how we know we need to switch these two. So this should be 10, this should be 4. So now if we go ahead and do FOIL one more time, we should have the same answer that we started out with. So this is how you can kind of guess and check. So first, we do s times s, which gives us s squared. Outer, s times minus 4, minus 4s. Then we do inner, s times 10, plus 10s. And outer, minus 4 times 10, which gives us minus 40. And if we simplify, we do in fact get the same trinomial that we started out with. So we have checked that this is the fully factored answer right here. Okay. Okay, so now a different set of questions. We have this function f of x, and we are given its graph. We don't necessarily know what f of x is, but we have enough information to answer the question. So we want to know what the function value of f of 0.5 is. This is also f of 1.5, or 1/2. So remember that this is our x value, this is our input, and f of x is our output. And graphically, this will be our y value. So what you want to do is first locate x equals 1/2. That is where we're concerned about here. So we have right about here, because this is 1, so right about here it's 1/2. And then what you want to do is you just want to either look up or down until you hit the function. So here we see the function's above, so we just want to travel upwards until we hit the function. And then I want to look over to the left and see what y value this is. So if we look on the graph, it should be 1. Okay, so our answer here, f of 0.5 is 1. So now we have a different type of function and problem where we're trying to find the limits. So we are mainly concerned about what x value right here, right? So we're really concerned as the limit of f of x as we approach, as x approaches 0 from the left, what is happening to my function? So 0 is right here, x equals 0. And we want to know what's happening to our function as we approach it from the left. So I'm going to trace my finger on the leftmost, starting on the leftmost part of the graph, and go left to right and trace along the function until I get to this point, x equals 0. And as I'm getting closer, I want to notice what my function is doing and what value it's approaching. And so it seems to be approaching 0, which it might be hard to see here. But this is the origin, which is x equals 0, y equals 0. So this is our origin where x equals 0 and y equals 0. Okay, so that is why when we look to the left, our limit is approaching 0. So now let's look at what happens to the function when we approach from the right. So I'm going to trace from right to left and see that my function is still approaching 0. All right, so that's what my function value is. And so now this one, notice how there's no sign over here. So that means that we want to know, is my left-sided limit equal to my right-side limit? Oops, right-side limit. So my left side limit is this one, and my right side limit is that one, and they are equal. And so their overall limit is 0. And you can see as my function tends to go to 0 when my x goes to 0 from both directions, so my overall limit is 0. And then the last question is asking, what's my function value equal at x equals 0? And so because it's continuous and filled in right here, remember this is the origin, 0, 0, my function value is also 0, okay? So for this problem, we want to know what the correct expression is using our limit properties. So I have the limit as x goes to -6 of 3x plus 8. So one of our properties allows us to break this apart into two limits based on that addition. So 3x plus the limit as x goes to -6 of 8. And then another property allows us to pull that 3 out because it's a constant being multiplied. So we can rewrite this as 3 times the limit as x goes to -6 of x plus the limit as x goes to -6 of 8. And so our answer would be C. Okay. And then the second part to this question would be to find what this limit is equal to. So x -6, 3x plus 8. So the first thing you want to do when you have a limit and you're trying to evaluate it is you want to just try plugging in this value. See if you get a number. So if we plug in -6 for x, we get 3 times -6 is -18 plus 8, and that gives us -10. And so that is a real number, so we can say that the limit as x goes to -6, 3x plus 8 is -10. So now let's try to find this limit if it exists. So again, let's just try plugging in this value, -2 for x. So we get 11 times -2 plus 12. And so we get minus 22 plus 12, and we get minus 10 again. And so that will be our answer here, minus. All right. Okay, so now we want to sketch a possible graph that has these qualities. So our function value, when we plug in 0, we get out 0, and then as we approach 0 from the left, we want the function to be going towards 2, and then as we approach 0 from the right, we want it to go to 0. Okay, so let's go one by one and see which graphs have this quality. So if I have this f of 0 equals 0, this translates to if I have an x value of 0, and then this is my y. So then I should have this point on the graph, 0, 0, which is our origin. So if we look at A, we notice that it's not filled in at 0, 0. So A is not it. B at 0, 0 has 0, 0 filled in. So that could be a potential answer. And same for C. See, that's also filled in at the origin. And for the same reasons for A, this is not filled in, so D cannot be the answer. Okay. So now let's go to the next condition. I want to look at what my function is doing as we approach 0 from the left. So let's start with B, now that we narrowed it down to 2 options. So I'm going to trace my finger starting from the leftmost part of the function, trace it all the way down as we get to x equals 0. And so my function is approaching, I believe that's 2. Each one of those grid lines is 1 unit, so that will be 2. So that's promising. Let's check if it has the third condition. So as we approach 0 from the right, is my function going towards 0? So I'm going to trace going from right to left, starting at my rightmost part of the function, going towards 0, and I notice that my function value is also tending towards 0. So B is our correct answer because it has all 3 of these conditions. You'll notice C does not, because our left-sided limit as we go towards 0 is 0, not 2. And if we look at the right-sided limit as we go towards 0, it's going towards 2. So it kind of has these switched. Okay, so B is the answer here. So let's do another one. So now we have these conditions. So f of negative 2 equals 1. So remember how we did this in the last one. This is my x value, and then this is my y value, right? This is my output. Okay, so that means that I want to have the point negative 2, 1. So let's look which graph has that point. So it's not really numbered well, but this is negative 2 right here, and this is 1. So A has this first condition, so that's good. So does B. You'll notice this is negative 2 and 1. C has an open point there, so because it's not filled in here, C cannot be it, because this is where the function exists at x equals negative 2, and that would be 1, 2, 3. So not 1. And then same here, f of negative 2 is 3. Okay, so now we're looking between A and B. So let's look at the second condition. So we want to see what happens to my function as I approach negative 2 from the left. So I'm going to start from the left, head to the right towards -2, I see my function is going towards the value 1. So the limit for a, x goes to -2 from the left of f of x is 1. Okay, so that can't be it because it should be 3. So now let's look at b. So I'm going from the left towards -2. So I'm going to trace it, follow it down, and I see that it's headed towards 3. Even though it's not filled in here, that's okay. You're just wondering what's happening when you get really, really close. Okay, so the limit as x goes to -2 from the left of f of x is indeed 3. So that's good. Let's just check the third condition to make sure we have the right one. Okay, so now we're going to -2 from the right. So I'm going to start at the right part of the function, travel leftward until I hit x equals -2, and I notice that the function is also tending towards 3. So from the right of f of x is also 3. So B is our answer here. Okay. So for this question, we have a statement here. If the limit as x goes to 1 of f of x is equal to 0, and the limit of g of x as x goes to 1 is 0, then the limit as x go to 1 of their quotient is 0. So if it's always true, then we want to explain why. But if it's not true, then we only have to provide one counterexample or one example where it fails. Okay. So let's see. So what are our options? Let's go through A. The statement is not always true. For example, the limit as x goes to 1 of x squared minus 1 equals 2. Okay, so a few things we need to verify. Does the limit as x go to 1 of x squared minus 2, is that equal to 0? Is the limit as x goes to 1 of the denominator, x minus 1 equals 0? And then is this limit true? Okay, so let's first look at this one. So remember, I always want to try to plug the number in that x is approaching. So this gives us 1 squared minus 1, which is 1 minus 1, which is 0. So this is true. Now let's look at this one. So let's plug in 1, we get 1 minus 1, which is 0, so that's also true. So now let's look at the consequence, which is this part, the then part. So alright, so now let's take the limit as x goes to 1, x squared minus 1 over x minus 1. So let's try plugging it in. So we get 1 squared minus 1, 1 minus 1. And that gives us 0 over 0, which is an indeterminate form. So what we need to do is we need to rewrite this function and do some algebra. So one thing I know is that there's a difference of squares in my numerator. Remember when we did this earlier? So difference of squares, a squared minus b squared equals a plus b, a minus b. So here my a squared is x squared and b squared is 1 squared. Okay, so we can rewrite the numerator as x plus 1 and x minus 1. We notice that when we do that, these can cancel, and we can cancel them because we're dealing with limits. Don't really care what's happening at the function value of 1, so we can cancel them. So now we want to find the limit as x goes to 1 of x plus 1. And so as always, let's try to plug it in. We get 1 plus 1, and we get 2. So this is true, and because this is true and it's contradictory to this is a counterexample to the given statement. And so that's why A is true. All right, so you could go through the other examples and try to figure out why they aren't true. D is not true because we just found that the limit does exist and it's equal to 2. So we know that D's out. And we know that the statement can't always be true. There has to be some situation where it may not be equal to 0. Alright, so another one. If f is a function such that f of x, the limit as f of x as x approaches 0 exists, then my function value at x equals 0 exists. So now this isn't always true, and what it's saying graphically is that I have 0 here. So graphically, one way that this can be a counterexample is my limit does exist here. Let's call it 3, but it's an open circle. So my f of 0 does not exist. So that's one way we know that this isn't true. So that's why I'm going to rule out the statements it's always true. Oops, we know that's not right. So now we need to look at A and D and what's the difference. The difference here are two different functions. Right, I have f of x, x over x squared minus 1, and I have f of x, x squared over x. Okay, so let's verify for A, or C for A, is the limit as x goes to 0 of x over x squared minus 1 equal to 0? And does f of 0 not exist? D and E. Okay. So what happens if we try to plug in 0? We get 0 over 0 minus 1. And so 0 over minus 1 is just 0. 0 divided by anything but itself is 0. So this is true. So now let's see what f of 0 is. Does my f of 0 exist? So 0 is in the domain of this function, and how I know that is because restrictions on the domain only occur when this does not exist, this function does not exist, and that would be when the denominator is equal to 0, because we cannot divide by 0, so our range, or our domain would be, let's factor x plus 1, x minus 1, so when x is equal to -1 and when x is equal to 1, our function doesn't exist. But none of these include 0, so we can do the same thing where we plug in 0 and find the actual function value. So 0 over 0 squared minus 1 is equal to 0. Okay, so that's why this one's not true, because f of 0 does exist. F of 0 is equal to 0. So probably not A, so let's take a look at B. Oops. Okay. So now let's look at B. So we want to verify, does the limit as x go to 0 of x squared over x equal to 0? And does f of 0 D and E? Okay, so let's try plugging in 0. 0 squared over 0 is 0 over 0, which is indeterminate, so we have to do math. Okay, usually algebra, so let's do limit as x goes to 0. So remember that we can cancel with limits. We can't cancel with functions, but we are able to cancel here. So let's cross out one of these x's here for the one in the denominator, and so we get the new limit as x goes to 0 of x. So when we plug in 0, we just get 0. So yay, this is true. So now we need to find what f of 0 is. Okay, so f of 0. So here, if we try to plug in, well, I guess, let's do, yeah, if we try to plug in, we get x squared, 0 squared over 0. Okay, indeterminate. But however, let's consider the domain of this function. So f of x equals x squared over x. So x cannot be 0. X cannot be 0 because if it was 0, we'd be dividing by 0. So then our domain is negative infinity to 0 and 0 to infinity. So it doesn't include 0. So that means that the function can't exist at 0. And so that is why D is true. Okay. All right, a new type of question. So now we are looking at limits with this form f of 3 plus h minus f of 3 over h. And we'll soon see that this is a form for the derivative, but that will come soon. So what I like to do for this one is I like to do on the side, what is my f of 3 plus h and what is my f of 3? Because we know that we'll want to substitute those into our limit. So h goes to 0, f of 3 plus h minus f of 3 over h. So my f of 3 plus h, remember that our f of x is this, so I'm just going to plug in, let's see, I'm going to plug in 3 plus h wherever c and x. And so I get 12 plus 4h minus 1, and so I get 11 plus 4h. And so I'm going to do the same thing for f of 3, and I'm going to get 4 times 3 minus 1, or 12 minus 1, 11. So then when I go ahead and plug it into the original problem, original limit, I have 11 plus 4h minus 11 over h. And so we can just do some math and simplify. 11 plus 4h minus 11, so those 11's cancel by subtraction. And we also, okay, so then h, let me rewrite it, 4h. And so now we can cancel these h's, and so we are left with 4. Okay. So let's do the same thing, but now our function's a little more complex, but not that much more. F of 3 plus h minus f of 3 over h. Right, so now we have the function f of x squared, or f of x equals x squared plus 9. So let's find our f of 3 plus h first. I'm going to put 3 plus h wherever c and x. So now let's expand that. So 3 plus h times 3 plus h plus 9. So let's do the outer, 9 plus 3h plus 3h plus h squared plus 9. And so if we combine like terms, and I'm going to rewrite it a little, h squared plus 6h plus 18 is what I got for that one. And then we also need f of 3. So let's plug in 3 wherever I see an x. 3 squared plus 9, 9 plus 9, or 18. So let's go ahead and plug it into our limit. So I have h squared plus 6h plus 18 minus 18 over h. And so let's do some simplification. H squared plus 6h, those 18s cancel by subtraction. And so I'm left with h squared plus 6h over h. Notice that we can take one of those h's out in the numerator and rewrite it as h plus 6 over h. Okay, and now we can cancel these h's, which is really nice because now we get rid of the divide by 0 issue. So then we have the limit as h goes to 0 of h plus 6. So if we plug in h equals 0, we get 0 plus 6 is equal to 6, and that will be our limit. Okay, we're almost done. 2 more practice examples for us. So here we have a car sharing service offering a membership plan with a base fee of $40 per month. That includes 10 miles of driving and then $15 times each additional hour. So if I drive 10 hours, my price will be $40, but if I drive 11 hours, my price will be the $40 plus 1 additional hour times 15. So just keep that in mind. So like I said, the 40 includes up to 10 hours. So that's why our piecewise function is 40 when x is between 0 and 10. But now if x is greater than 10, my additional hour is $15 times that. So it's not exactly just x though, because I'm only concerned about the additional hours. So I'm going to subtract out 10. Okay. But remember, I have to include this base price. So I'm going to do 40 plus. And so if I do little simplification, I get this minus 150. And so 15x minus 110. And so then can't fit it there, so I'll just do it over here. So my piecewise function is 40 if 0 and 10, okay? And then if I need more room. If my x is greater than 10, my function takes on this. So now we want to find a graph that corresponds with it. So let's first look at this first half. So when my x is between 0 and 10, I want my function to take on values of 40. So let's look at our graph. So here, this is about 40. So from 0 to 10, my function is 40. So a checks out. B is similar, so that also looks good. C seems to have a value maybe of 110 between when my x is between 0 and 10, so that's not right. And then in D, it doesn't seem to be a constant number of 40 here, right? It seems to be some kind of decreasing function, so D isn't right either. Okay, so now we have to notice the only difference between A and B right here is whether this endpoint is filled in, right? And that is determined by our range over here, our x range. And because this is less than or greater to, because this is less than or equal to 15, that's why we pick A, because it can include 15, and that's why this wants to be filled in. Okay, so now we're just gonna do some limits like we did way back when, based off a graph, because I put this graph here from B for reference. Okay, so here we are interested in, looks like x equals 10. Right, we have the left-sided limit, the right-side limit, and the overall limit. So x equals 10 is right around here. So for this first part, I want to look what's happening as x approaches 10 from the left. So again, I'm going to start from the leftmost part of the graph and go towards 10 from left to right. And I notice that my function is approaching 40. Right, so 40. And now I want to track from right to left for the right-sided limit. And that is also approaching 40. And so for the overall limit, because these two are equal, my overall limit is also 40. Okay. All right, our last application problem, it's kind of similar, but there's a little difference here. So a state charges polluters an annual fee of $30 per ton for each ton of pollutant emitted into the atmosphere, up to a maximum of 2,000 tons. And there are no fees charged beyond the 2,000 limit. Okay, so we want to write the piecewise function for when x is between 0 and 2,000 tons. So we get that from this piece. We get it from $30 per ton. And remember, x is the variable of the tons of pollutants in the water. So 30 per usually means multiplication, and then x is our tons. So our first part of the piecewise function is 30x if x is between 0 and 2,000. Okay, so now if x is greater than 2,000, what is my function? All right, so this piece comes from the no fees are charged for emissions beyond. So that means that whether your emissions is 2001, 3,000, you're going to be paying the same amount, and that amount will be 30 times the maximum, which is 2,000. So 30 times 2,000 is 60,000. And so this is our piecewise function. So now we need to use this piecewise function to find this limit as x approaches 2,000. So we need to consider x approaches 2,000 from the left, and what happens as x approaches 2,000 from the right. Because if they're equal, then we have an overall limit. Okay? So our piece on the left will correspond to x values less than, so my x is going to be less than 2,000. And so this corresponds to this piece of the graph, or the function. All right, so my 30x. So I want to find the limit of 2,000 of 30x. And so we're going to plug in 2,000, see if we get a number. And we do, it's 60,000. So that's our left-sided limit. Okay. And then now we want to consider the right-sided limit. So now our x values can be greater than 2,000. So now we're going to look at this part of the graph. And so we want the limit as x goes to 2,000 plus of 60,000. So because there's no x value here to plug in, this is our limit. It's a constant function. It will always be 60,000. Okay, and so now since our left-sided limit and our right-sided limit, they're equal, we can say, hopefully with confidence, that our overall limit is $60,000. All right. So now we can play the same game for this last part. What is the limit as x goes to 13,000 of f of x? All right, so let's look from the left and then let's look from the right. So from the left, we're considering values less than 13,000, but really close. So maybe 12,000 between those. So we would use this part of the graph, or the function. So we would find the limit as x goes to 13,000 left of 60,000. And so like we saw in the last problem, it's going to be 60,000 because it's a constant function. Okay, so keep that in mind that we got 60,000. And then if we look from the right hand side, now we're considering values greater than 13,000. And based on our function, we will still use the same piece of the function, so our limit is still 60,000. So our overall limit is 60,000 because the two are equal. And then 60,000. So if you're a graphical learner, we can use a graph to confirm what we just found using algebra. So I have a graph. I'm gonna be crazy, but basically when x is equal to 0, my f of x is 0, so I know that it's going to start here. It's going to have some kind of slope of 30x. It's going to be a straight line. And then once we hit, this is say 2,000, oops, extra one, then it's going to plateau off at 60,000. All right, so for this part, we were looking at what the function was doing. As we got closer to 2,000, we noticed that they were equal and it was 60,000. And then for the second question down here, we were looking at 13,000. X was approaching 13,000. So again, the function as we go from the left and to the right, it's approaching the same number, so our overall limit is 60,000. All right, so I hope this review helped, and I will see you in the next section.